conduct a coronavirus test. But it has not been conducting tests. They have created a new facility that can now conduct tests for suspected cases of COVID-19.
Hello.
We talk about public health in the state, and here's what is the impact of the facility environment.
I don't know if everybody can see the slide. You know, day before yesterday, we stopped the discussion on calculating sample size for descriptive study, and we also consider different outcome, that is, whether the outcome is categorical or quantitative. So we're not going to dwell much on that again. But the only thing is that I said that if I demonstrate something yesterday, that 50-50 gave us the maximum variability. 50% gave us the so the highest sample size you can calculate with descriptive study, every other factor remaining constant. If your Z is 1.96, that is at 95% confidence interval, that is your level of significance is 0.05, which is 5%. Then your level of confidence is 95%. Then if it's 2T, your Z will be 1.96. And if your maximum error of estimate is 0.05, which is 5%, and you are now 50-50, that is, the prevalence of the attribute, you just assume it is 50. In the situation where you cannot find a study, a previous study that give you the estimate of the prevalence of the attribute. In that case, you choose 50. If you choose it, this is what you get. 384.16. Go and try it. That's what you will get. That is when maximum, every other thing remaining constant. When maximum variability assumed. Just put in 1.96 squared and 0.5, that's 0.5, because 1 minus 0.5 is 0.5 also. Divided by 0.05 squared, give you 384.16. That's maximum variability assumed. So without wasting that, let's quickly go to situation where you are calculating sample size for analytical study. In the sense that it's not just only one group. You may have 2, 3, 4, as many groups as possible. And the group may be before and after, in the sense that it's the same group of people that you are studying, you are collecting your data from before and after on 2 occasions or 3 occasions. Whichever way is analytical study. So a lot of factors we talk about as determining how you calculate your sample size come into play here. So the way you calculate the sample size now depends on number of groups you are dealing with. The number of computation is called the number of possible combination of the groups. You can only, when you are talking of difference between groups or among groups, you can only find difference between 2 groups at a time. In that situation, if you are having 3 groups, what you do is to pair them in 3 different ways. Of course, how many number of ways can they be paired? And you need to calculate sample size for each of the way, and now choose the largest. For example, if there are 3 groups you want to study, if there are 2 groups, it's only that is you are going to have 2 samples. You are going to have you can pair 2 things in one way. A and group, 1 and B, urban, rural, private, public. Just pair these ones. But when you are having 3 groups, there are 3 possible ways. A, B, C, 3 groups. A, you can pair A with B, that is one way. You can pair A with C, that is another way, second way. And you can pair B with C. That situation now, 3 groups can be combined, paired, they can be arranged 2-2 in 3 ways. And when you are finally looking for different, the different may exist in between these 3 pairs, anywhere between. So in that situation, you may need to take that into consideration. You pair them in this 3 ways and calculate the sample size with each pair. So after doing that, the one that gives you the largest sample size is what you're going to take for each group. The reason is very why you may ask, why should you take the one with the highest, why not the smallest? You know, it's the minimum sample size. It can be higher, but it must not be smaller than that. Because if you go below the minimum sample size, if you eventually did not find the difference you are looking for, you are not sure maybe the difference does not exist, or it's because it exists, but your work is not powerful enough because the sample size is too small to detect the difference. In that situation, where the minimum size, you must not go below minimum, but you can go above, but not below. So if you pair 3 groups in 3 ways, and you try to calculate the sample size, those are the different ways you can look at the difference between them. When you calculate sample size 3, you get 3 computations. Those 3 computations, if you go and choose the one that is not the largest, or maybe the smaller, or the one in the middle, that particular group pair that has higher value, it shows that if you carry out your study, you may not be able to find the difference between those 2 pairs and the pair. That particular pair that is the highest that you have neglected, you may not be able to find the difference if it exists. So to be on the safer side, you choose the biggest one. When you choose the biggest value, it's suffice for that pair, and also for the other pair that are lower. After all, it's minimum sample size. You can go above. And what you have there as a table is just to employ the formula for logic behind combination of group or items. So you can combine different number of items in R way. You know, the original formula is C combination, N combination R. So how many times can you arrange? Maybe 10 times in 10 items, arrange them 3 by 3. But in this case, we are not talking of 3, we are taking of 2 by 2 because we are talking of pairing. So how many times can you arrange 10 items or 5 items or 6 items by pairing them? That is what this one shows. Because in calculating the sample size, looking for difference between groups, you have to pair them, take them 2 by 2. So if you have 2 groups, we have already said it's only one way. Look at it. The formula gives us 1 number of pairs of possible. That is number of the computation you're going to have. So if there are 3, I've already said it, that's 3 combination 2. How many ways can you pair? We have already said 3. If you calculate it, give you 3. If there are 4 groups, you can pair 4 groups in 6 ways. That shows that you're going to calculate 6 samples. Use them in different pairs to calculate, to be able to get the largest value to use as your sample size. Then you can, if it is 5, 10, and if it is 6, 15. If you look at this pattern, it recall when we discussed Neman-Barker chi-square. It also recall when we talk of ANOVA. So you see, it's the same logic. Try to pair different number of items. Then let's quickly look. We've already established the fact that we are going to pair them in different ways and calculate, and now go with the highest. So in other work, all you need to do is to know the formula for calculating sample size for 2 groups. For 2 groups. If there are 3 groups, it's just a matter of you pairing in a 3 way and calculate, assuming each pair is 2 group on its own, and calculate. So, and the same thing that is applicable to calculating sample size with descriptive study. It's applicable here in the sense that the outcome measure will be considered. The outcome measure may be quantitative, may be qualitative. So on the left side, the first side of the screen, you see is for categorical, that is comparison of proportion. When you talk about proportion, you are talking about categorical variable. Proportion, that is percentage. So it's categorical variable percentage. Then on the right side of the screen is comparison of two means. This one is two proportion. The formula is done. You will now notice when we're looking at the formula for calculating sample size for descriptive study, we may mention of the fact that power is not represented in that formula. Power. Because you are not actually looking at difference between two groups. Since power is your ability to detect difference, then you are actually making an estimate. You are trying to estimate for descriptive study, you are estimating the population parameter. But in analytical study, you are trying to look at the difference between two. Though the issue also you are somehow estimating the difference in the population. That different population is a parameter on its own also. So it's still estimating, but this estimation now is different in the sense that there are two things you are estimating at the same time, and you are looking at the difference. So the two, maybe it's proportion. The two proportion, they are parameters. Even the difference in the population is a parameter. So when you are having that to calculate the sample size for two groups, study involving two groups, you are estimating the attribute, the parameter in the population for each group. At the same time, also, you are trying to see, do they differ? How much are they? The difference going to be significant. So that is why, because of that different issue, trying to do different, you are looking for the difference. And that is what the description of power is. And that's why the power criteria is in that formula. You can see Z alpha is the standard normal deviation that corresponds with the significant level. We have talked about it 2 days ago. So if you set your level of significance to be 0.05, which is 5%, that shows that you are 95% confident. Because the confidence level and the significance level add up to 100%. So if your level of significance is 5%, your level of confidence is 95%. And for both of them, each of them, the corresponding Z is 1.96 for 2 T test. Is 1 T 1.645. Now, Z alpha is the standard normal deviation that corresponds with the level of significance. C beta is standard normal deviation that corresponds with power, or 1 minus power. Actually, 1 minus power. That is correspond with the beta. The other one corresponds with the level of significance, which is alpha. The power, the beta is not power. It's actually complement of power. That is 1 minus power. You can see both of them, the way they are related. You plus them, you add the two together and square. You will still see that both the Z alpha, Z beta, and the prevalence of the attribute and the multiplication of the prevalence make the numerator, while in the denominator you see find something like the difference between two groups that are considering. Sorry. So the numerator is the difference. If you look at it, I wrote in it two way. It's the same because unless you understand the formula and look at it closely, you see many books they write it the same thing but in different way. Another person may write it, may not call this alpha or beta, you use another. Some people even use other letter A and B for Z alpha and Z beta. They use A and B. It's just for you to see what is the description. when you use something in the formula, you have to define what each of the item in the formula means. So here now, describe. If somebody use A and B, just for you to describe those elements in the formula, you will see that P1, P2, because there are two populations. In that way, correspondingly, there will be Q1, Q2, because P1, you remove P1 from 1, you get Q1. You remove P2 from 1, you get Q2. So the P minus P1 minus P2, some people go and write P2 minus P. It doesn't really matter because maybe you realize that the P1 is bigger than P2 is bigger than P1. No, because it's denominator and you are squaring it. Since it means square, it's not because it's denominator, but since it means square, it will cancel the negative. It doesn't really matter which one you put first. You can put the bigger one as the bigger one can be P1, the smaller one can be P1. Doesn't matter. If you remove this bigger, if you say smaller minus bigger, to give you negative, but it doesn't matter because you are going to square. There is a square there. When you square negative, it becomes positive. So if you see the alternative one wrote there, D square, that P1 minus P2 is the same thing as D square. And if you come to this side of the equation, so M1, which is the mean, minus M2 is the same thing as the D. As D, M1 minus M2 square, D square. So the D is the minimum expected difference you are looking at. So you can as well say is D or the difference between the two groups. You remove proportion of one group from the other one. That will give you the difference. Or you remove the mean of one from the other one, it gives you the difference. So it doesn't really matter. So now, if you come to, if your outcome measure is proportion, is a mean and standard deviation, you look at the right side of the screen, you will see that the only difference is actually either you are dealing with P1, PQ1, PQ, rather than this one standard deviation. So that's the only difference. So it's very straightforward. I can even say that even for two group study, it's more or less more straightforward than one group study, the way I see it. Now, let us go to.
Hello, sir. Hello, sir.
It's not the time for. Let's finish before you ask question. You can type your question. Let's finish before you. Let me quickly finish. I'll give room for question. So that's just that. Now, what I just described now is when you're having the two group independent. But now you may have the two groups dependent. That is the same set of people, the same set of subjects that you're going to take before and after measurement. In that case, the formula differ. You may not bother yourself with the complexity of the, because the logic is just for you to know which formula to use now. And if you are, well, if you want to, at least to have an idea, if you are using software to calculate, to have an idea that this is what I'm dealing with. So if you look at it, even the one that is simplest mode to me is when the outcome is quantitative. If you look at the outcome categorical, this you multiply this by this one, square root of PQ square. This square root of PQ, so Z alpha plus Z beta plus 2Z beta, then times square root of PQ square all over 4 PD. PD is sum of the proportion of unmatched pairs for the two groups. So all you need to do, because sometimes if you begin to explain, well, to me it doesn't make any much difference. Just get this right and put in. But even many people now, they don't even bother people about understanding the formula. Just say, feeding this area now. When it comes to observation, just enter into because some regular mathematical operation brought out this. Just enter into software, let the software give you the answer. But nevertheless, I want to explain something under this comparison of mean in peer group when the outcome is quantitative. You will see what is standard deviation. You see there is standard deviation of the different. I think I explained this thing last week, Thursday. If so, yeah. Last week, Thursday. The mean of the different is different from the difference between mean. If you look at the previous one, when you are dealing with two independent group, like this the first slide here, two independent group, the mean you are getting there is mean of different group, two group. Let's say two group. Now the D, which is M1 minus M2, is the difference. So it's the mean of the difference. That is, you calculate the mean, the difference if they say the one mean is 30 and the other one is 35. What is the difference between 30 and 35? The mean difference. No, not the mean difference. The mean of the difference. The difference of the mean, between the mean, rather. Different between means. Yes. You have calculated the two means. Now look for the difference. Difference between means. That is independent. But if you come to dependent, what you are seeing there, look at the standard deviation, is the D here you see, is not just the difference between the group, is the mean of the difference. Because if you take the measurement on two occasions from the same set of people, for each person, you can minus one measurement, the first measurement from the second, or the second measurement from the first, whichever way, any of them. The difference between them for each of the elements in that sample. When you now calculate the average, the mean of that difference, that is what is being said there. And that is what you actually, when you talk about PAT-test, it tests the mean of the difference. While the independent tells the difference between means, the difference between the two means. That's what the independent group tests. While the dependent group tests the mean of the difference between observation before and after. I think it's very clear. And once you get that one right, I don't think you should be square about the part. It's very simple. It's the simplest. Once you get the concept right, it's the simplest. You say I put it as a mean value of the difference between the two observations. So somebody, the person that was say hello, let's just stop here today. So question, we still come by next week, maybe by Tuesday, that's when we'll do the last grand finale for this sample size. We'll consider special situation. Special situation. If you look at what we have just done now, the sample size you see here does not have respect whether it's a experimental design or not, because that one is not relevant. What is relevant? The experimental design can be in any of these forms. It can be two or more than two. It can be independent group. It can be dependent group. And your outcome measure can be categorical and it can be quantitative. So whether it's observational study or what do you call two group observational study, what do you call comparative study, or you call it cross-sectional analytical, or it's experimental design, it's surface. So just for you to know what you are dealing with. Then you see that this observation, most of that is common with experimental design, but it's not exclusively for experimental design. It's only that it's very common with experimental design, and people now think maybe that is the method used in experimental design. Who is making noise? Coyote. So now think is the method used in experimental design. But this special situation, like case control and cause study, that's what we're going to do next week, and also talk about the some effects, like the design effects some people are asking about. when a lot of things, the situation where you don't, when the way you select, it's more of select. Though sometimes your study design, the way you have designed your study from ab initio may affect your selection. So the way you select, we talk about selection bias the other time. Is the way you select that brought out that that design effect. So that if you don't follow the simple random sampling, so you are likely to have that effect. No cluster sampling. Cluster sampling is not simple random sampling. Sometimes when you use, apart from when the probability of each of the item being selected equal 1, is equal. It's not equal rather. When the probability is not equal, it has deviated from simple random sampling. So in cluster sampling, the people in one cluster, they are more likely to have similar measurement than the people in other clusters. So they will have what we call intra-class correlation. There will be correlation among them. And that one has a way. You need, for you to overcome that, you need higher sample size, because in a cluster, if you have 8 people, 8 people may be behaving like 1. In fact, though in your sample they are 8, but they are actually 1. The sense that what they are contributing to is 1, because the measurement tend to be related. What you are getting from it tend to be the same. So there's no variability. And it's the effect of variability that helps you to get answer to your research question. The effect of variability, but in a situation where all of them are the same, they're not giving you new thing. Imagine if you are asking people many questions, you are asking them something, you expect different responses for you to get different idea. And all of them are telling you the same thing. You say, no, these people, they are not giving me variation. There is no variation of what they are giving me. So I'm not learning anything new. But they are telling me the same thing. So there is this inter-class correlation. So we call it design effect. That's not the only cause of divide. We're going to talk about it and have some pictorial infographics on that. Yes, I think we can stop here. Somebody, the person that was asking question, what is in sample size estimation? Okay, that's what I just said now. First, I've had you mention 1 minus power that you explained. Thank you, sir. I think I explained this thing last week. Beta is 1 minus power. I explained it last week. Let me just quickly go back to that slide. The slide, that 1 minus power. So, I know that some people they are joining for the first time now. They were not here 2 days ago, rather. I think I show something like this.
Yeah.
I show something like this. I say
Yes.
I said number 1, power usually one case, so one side. This one is power of 80%. We talk about when the I show beta. I say this is the I show any other thing. Yes, I think that's what I showed about power. Look at okay, make it, let's use that 2 thing and 1 thing. I said that I think I explained extensively. When we talk about significant criteria, we talk about the whole, I explained that the whole of this graph is 1, this normal distribution, because it's a probability distribution. So the best way, because you cannot know the probability of every outcome. You cannot even know the possible outcome. Any in a situation where you cannot know the possible outcome, you cannot know the probability distribution of all the possible outcome. And probability distribution is the value of all the possible outcome of a variable and their probabilities. In discrete probability distribution, it's possible to know that all those things are categorical. They follow discrete: sex, ethnicity, all those marital status, maybe professional group. Think of anything that is categorical. They follow discrete probability distribution because you know the different categories and you can calculate their probability just for you to know how many in each category over the total. It gives you the probability. And you don't know that when you show your result, the probability distribution you are showing, when you tabulate your results and you put your percentage, everything add on to 100, you don't know the probability distribution. You are telling us, you are showing us the different categories of the outcome. For example, maybe ethnicity. You have listed them, and I put the percentage of each of them. The different category is the different value outcome of ethnicity, and the percentage and the probabilities. So that is probability distribution. But you cannot do that for continuous variable. Please, if like blood sugar, like age, all those, you cannot do that. You cannot have a table for it. Any table you see, you categorize. Is no more age per se, it's age group. When you group, that age group categorical is not the real age. Age group is not the real age. Whenever you group a continuous variable and then put in category, is that in category. It's not the real. It's no more. It's a that one age category. Age group is a categorical variable. So you cannot be listing and say in the table you list all the this and the percentage, because all the one you even have in your study, the value, they are not the only possible value. So you don't have denominator to know all the possible value of age or blood sugar. In that case, you cannot tabulate it and say it is a probability distribution for that age. Then you can only talk about probability distribution of the age group. So in that case, few intelligent people, that's okay. The best way to show a diagram, probability density function, just show the graph, and that's okay. This graph, let's just consider it to be 100%. Just like somebody, when you bring bread is 1. That one bread, we divide it into 2. Equal half. 1 is half, 1 is half. You want to divide it to 1/4 for 3 or 4 equally, 4 of us equally. That's a 1/4, 4 places. So, but the fact is that either the bread is a big bread or small bread, but we just have one bread. So we should divide equally. So it doesn't really matter the size of the bread. So far, that one bread is 100%. We cannot divide into different components. It's the same thing. So these intelligent people now plug this guy, and to be sincere with you, among all the continuous probability distribution, the graph, the normal distribution is the most popular and the basis for hypothesis testing. And it's easiest to even illustrate all this thing, because number one, if you say, okay, the area under it is 1, yes, the area is 1. It represents the total probability, because probability cannot be equal to, it cannot be more than 100%. It cannot be more than 1. So, and it's bilaterally symmetrical. You divide it, one half is other half is the mirror image of the other. So in that case, it is easy for you to use it. So what they just use that, okay, if we say level of significance is 5%, and it corresponds to level of confidence, and level of confidence and level of significance add up to 100%. So if you now look at the graph now, look at the area that constitutes 100%, 75%, the remaining 5%. So that remaining 5, if it is 2T, the remaining percentage will be at the extreme end, 2.5, 2.5. The middle 75% will be the confidence level. If it is 1T, the confidence level 95% is to one side, the 5% your level of significance is on another side. So when you now read along, so for you to know where the positioning of this thing, so instead of talking about the probability now, yes, you already know 75% in the middle, and then the other one, which is your level of confidence, the other one 5%, 25, 2.5, 2.5 on both sides. If it is 1T, 75% on one, 95% on one side rather, and the other one is 5%. So for 2T, for you to move to where, if you look at this area now, if they split it to 2, for you to move from 0, because you can move from 0 to negative side or 0 to 1 positive side. It's not actually positive or negative, it's the way we did it. Because in the real value, that one that are negative are values that are below the mean. The one that are positive are value. So negative here mean does not actually mean negative value. It means that these are measurements that are below the mean. The positive are the measurements that are above the mean. The mean is at the 0, is in the middle. So that the negative is not actually value, it's more like sign. So now you can move from middle. If you move from middle to where the 75% of the graph stop. In 95 rather, the percent of the graph stop. So they say that along from 0 is the Z, because Z is measured along the line, is 1.96. If it is 1 T, where the 95 is on one side, you can see this area here now is bigger than this one. So you don't expect that movement from 0 to reach 1.96. It will be 1.645. This is for 1 T, 1.645, 2 T, 8, 1.96. So I explain so that you can understand the power. The power is usually one T. It's usually 1 T. The significant level can be 1 T or 2 T, but the power is usually 1 T. The same logic. So if that's okay, if you see power of 19, that shows that 90% of the graph on one side has covered. So where if you move from 0 to that place where that separates 90% and 10%, the remaining 10% is 1.28. That is what you see here. Look at this here, 1.28 on this table. 1.28. But if your power is 80%, so that point that separates the one side 80% of the graph to the remaining 20% of the graph is going to be 0. It will have reached this place. The 80% will be around maybe this place. From 0, from the origin, it will be 0.84. I think I demonstrated it. 0.84. So when you look at it like that, or you look at it 0.842. So when you look at it from that, so when we are talking of beta, the beta is here, the smaller part. So if we say that that 1.96 Z corresponds with alpha, that's level of significance. So this one corresponds with the beta, because when we are talking of why is this not moving? So when you are talking of, if it is significant now, we are talking of beta. The beta is the level of significance. So that's alpha type 1 error rate. But if you are talking of beta, that is type 2 error rate. So if you say 1.90 corresponds with level of significance, the one for the 0. This 1.28 here actually corresponds with beta. But that beta is 1 minus power. That's why they talk about 1 minus power. I don't know if it's very clear now, because the person that was asking the question, I know that whenever you ask that type of question, unless you have a pictorial explanation, somebody just talking to the air, you may not get it. So, yes, any other question? Have I answered the question? The question about the design effect, we talked about it Tuesday. We merge it together with the determination of sample size for quad and case control study, because there are special cases. If you look at those case control is a special case in the sense that you have already identified the cases, the outcome. You start from, it's like working from answer to question. So you want to know the factor that is responsible for a particular disease. So the factor, you have already gotten those that have the disease. So you are now looking for, you need just have to, just selecting. You have to consciously, not just select. This one not just by simple random sampling as they talk about like that. It's not just like that. You must be able to locate appropriate match. So in that case, a lot of factor influence is not just simple as it. That's why it has a special consideration for sample size. The same thing with cohort study, where you have a group of people that are cohort that are doing, they are exposed to a certain factor. You want to know, okay, how the factor lead to development of a particular disease. In this case, now gathering those cohorts that are exposed to a certain factor, and you still want to now look for other people that are not exposed to the factor. Can you see? So it's quite different from the other. Even experimental design, you can just get people by simple randoms and now randomize them and now divide them by chance into different groups, and you do your career experiment. But case control was studied their special consideration. Okay, that's great. Any other question? Any other question? Okay. If there's no question, that would be okay. That would be okay. If you don't want to ask, you can text. I will not read your name. I will just read the question and answer it. So if you are here also and your number is not on our WhatsApp, you can shout it privately. You don't want people to see your number, just shout it privately to me. If I hear your number is not on our WhatsApp list, so that you can easily get all the information.
Good evening, sir.
Good evening, sir. Yeah, good evening.
Yeah, good evening. Please, sir, I just request that you put this sample size session on the website, sir.
No, it's
they
there.
Have been wonderful.
No,
this session.
This session is going to be there. It's going to be there. It's recorded. It's going to be there because the initial one we have put 2 of them. It's only one of them did not record very well. But that's why I tried to repeat everything I did in those. I repeated some of them. So it's there.
So I must say, the sessions are just very wonderful.
Okay,
I have not had sample size discussion as deep as this.
Okay,
so please, I just request help us to put it on the website so that we can have opportunity to listen to it over and over again.
Yes, we put in the first 2. If you look at we have uploaded the first 2 there. The first 2 are there.
You,
one and two. This one will be number 3. Okay,
all right, great. So great.
Welcome. Any other question?
Hello, sir.
Go on.
Hello. Yes, sir. Thanks so much for the wonderful lecture. Sorry, I just want to make a very clear clarification rather.
Okay.
For the second formula you gave us for independent, I was thinking those formulas were for analytical cross-sectional, but you made mentions of descriptive. So at that point, I was a bit confused. That's why I called immediately to, I make a reference immediately to clarify that point. Because I mean for analytical cross-sectional, I mean with a single group, but with control. So,
okay, thank you. This, I don't know what you mean by or cross-sectional analytical study. Maybe that's what you want to say. Cross-sectional analytical. That's what you call analytical cross-sectional. Cross-sectional analytical. Well, if you this issue you just raised now, I was discussing with somebody today. Because I discussed with somebody last night on the issue of sample size determination. There is no, cross-sectional study with control. Apart from when you say case control study, then we have core study and the control, the experimental design with control. Actually, there's no cross-sectional study with control. It's you that just brought they have one group design, they not just say, okay, and let that be control. So if you are going to do a study that is one group, this formula, the initial formula for one group, descriptive study, that's all. So the only thing you have to consider, okay, is your outcome categorical or quantitative. So there's nothing like actually cross-sectional study with control. Some people after they want to study one group. Some people now suggest, why can't you have a control? If you want to have you want to have 2 groups, that will be what you call analytical, cross-sectional analytical study, or what some people they do, it is where you can. I think the best is cross-sectional analytical, but it comes with variances because comparative study is a form of cross-sectional analytical in the sense that there are two groups. So what you actually do is descriptive study for each two groups. But whenever you are now doing two groups, you are comparing to two groups, it's no more descriptive. Though it's cross-sectional, it becomes analytical in the sense that you are comparing two groups. There's a comparison group. There is cross-sectional study. That's what makes it different from case control, cohort study, experimental design. So experimental design is not a cross-sectional study. The case control is not a cross-sectional study. Cohort study is not a cross-sectional study. But all those ones, they have control. Experimental design has control, but there are some design that the same group control for itself. The case control, as the name implies, we have control case group and control group. Cohort and the control group. Those are the ones that come with control. But whenever you are doing descriptive study now, cross-sectional study, and it's one group, it's now descriptive cross-sectional study. If there are more than one group, it's cross-sectional analytical study. It can be comparative study or repeated cross-sectional. Both of them are cross-sectional analytical. When you say repeated cross-sectional, you take sample now, you also take one on the same group of people later. You are now analyzing the two. In that case, it's repeated cross-sectional. It's a cross-sectional analytical study. A comparative study that you do, two group, cross-sectional, a cross-sectional analytical study. Analytical, the word analytical, there must be comparison. That is, there must be more than one data set you are running. Once you are running two, it may be, the two may be from different group, which we call independent, which was the first one I was explaining. Independent group, this. Then if it is dependent group, the same group person, but you take measurement more than one, that is this second one. So if you look at it, whether you are having two separate groups or before and after, you can see it in observational study, what we call this cross-sectional analytical study, that is comparative, if they are two independent, comparative. If it is repeated measure, it's before and after, it's cross-sectional analytical study. It can be in experimental design. The issue they have told you, by design, experimental study have comparison group. It has comparison group, that's by nature. There's no experimental study without a comparison group. It's not possible. You cannot take measurement once and say you are doing experimental, because that is why it is experimental, because there's something you do which you have to be sure. You must take measurement more than one to be sure that it is what you do that causes this change you see. If you didn't take measurement more than once, it's not possible for you to know. That is why by nature, the experimental design it has comparison, it's analytical. By nature, experimental design is analytical. But not all observational studies are analytical. Some are descriptive and the rest are analytical. So the sample size determination we are having is for analytical. It has no respect for whether it's not a matter of whether I made this experimental or not. It's a matter of, are you dealing with comparison? You have group you are comparing as far, it's not only one measurement. And this measurement can be for independent group, or it can be before and after. And all of them occur both in the experimental side and the observational side. That is why all the formula I've described now has no respect for whether it's experimental or not. So, though there are many design, maybe we still talk about crossover design. The crossover design is the same thing. Like this one, you have two groups. You now do one, your intervention for one, you have two different interventions. You give one this or later you cross it over. The issue is that when you are breaking them, you have these two groups. When you analyze it, you are analyzing two separate independent groups. If it is repeated measure, that is the same group before and after. Even some people can even have two groups, and you still do before and after. People will do whichever way. So I don't know if I have answered your question. So any other question? Any other one? Okay, if there's no question, I think you can put. So that means a single group with control is still descriptive and not analytical. Where somebody says something. Yes, where you cannot say that if you now bring control in, is analytical by nature, because by the time you are analyzing the two, it's analytical. But what I'm saying is that you don't call it control. There's nothing like single group with control. You rather, it's because some people just come with strange idea. Somebody you started off with single group. Some people say, come on, hard control. That's not the way to if you actually want to get evidence that is reliable, if from the inception you make up that's the essence of your literature review. You look at the research question, you look at it critically, the best way to answer the research question. Let me tell you, there's no such design that is superior to the other. They just say that, okay, the evidence you get from different study vary in the strength. The strength of the evidence is what vary. Is the strength of evidence. No study design is superior to the other. It's the strength of evidence that vary. For particular, for treatment now, you say experimental design. It gives the strongest evidence. It doesn't mean the experimental design is superior to the other one, because there are situations where you need to do experimental design. There are some situations you need to do observational. Even there are some situations you want to do experiment where you are constrained by ethical reason. You do observational. Even when I usually give example, for many years, they demonstrated that low dose aspirin prevent death from cardiovascular disease. And a lot of results of randomized control trial prove that. And even you read the meta-analysis also demonstrated that. So people started prescribing, physicians started prescribing low dose aspirin. But later, another study found out that more people even die from breathing disorder than from, they will have died from cardiovascular disease. Why? Because they did experimental study to demonstrate, many of the experimentals to demonstrate the same thing. But what people forgot was that whenever you are carrying out experimental design, for example, part of treatment, most of the time what you are able to get is efficacy. That is the effect of that thing in ideal situation. But the ideal situation does not occur in real life. We are doing study, epilepsy, exclusion criteria. Epileptic patient not allowed, hypertension not allowed, diabetes not allowed, sickle cell not allowed, asthma not allowed. All those things not allowed. You finish your study. Bleeding disorder not allowed. You finish the study. Oh, you have demonstrated. But in the real life, when people that are using the particular treatment, some of them they have the heart disease, they have the condition, they also have epilepsy. They have the condition, they are also sick. They have the condition. So at the end of the day, when they use it, the effect, what they get in the study is not actually the same thing in real life. So you also need a follow-up, a observational study to follow up. And that will be even very more expensive than the experimental design, which number one is not usually done. And many people suffer, some people suffer for it. Just give it like what example of people that die from the low dose aspirin. So those are the issues. So no one study design is superior to the other. So I'm not saying that if somebody now bring the second group is not analytical. By the time you give me two groups to analyze, I know it's analytical. It's analytical because I have to give you, even by the time I'm describing, normally just doing the frequency, I have to be putting the p-value to compare the two groups. But what I'm just saying that ab initio, you will have study, design your study in a proper way and call it proper name. Is you call it comparative study, or you call it cross-sectional analytical study, or repeated course, or whatever you want to call it, the proper way. Rather than it's okay. Well, some people just call it, say case control. They are doing comparative study, they call it case control. They don't know that case control has to do with case of a particular problem, and then you now get the control that are similar in many respects apart from that problem. And then you now begin to ask questions about what you think the factor might be responsible for that problem. That is case control study. So you cannot just do, people just do, they set up to do cross-sectional study and somebody say, okay, put control there. Maybe you are saying you are looking at, you're like what I discussed yesterday with somebody, looking at among in the orphanage, you want to study their maybe the cognitive function, or you want to study their serum iron. Yes. Then somebody will say, okay, why do you choose, okay, if you get it among, then why, okay, why not compare heart control that are not orphan? So at the end of the day, they will not say it's case control study. They say the case is orphan. No, that's not true. Because if the case is orphan and the other one is control, then your question should be telling me what caused the orphan. If the case is being orphan, your question should be directed, your such question should be addressing the cause of the orphan, being orphan. And you see that? So you need to understand. Most of the time, it's comparative study you are doing, which is cross-sectional analytical. You now say they are just doing it, it has control. They cannot call anything. You know, eventually, now say it's case control. So those are the things I was just highlighting. I don't know if so I don't want anybody to be confused. So I think if there's no other question, we can stop here. Let me just.
Thank you very much, sir.
Okay, you have
very
question?
Wonderful section.
You have question? No, right?
No, sir. No,
you
sir. I'm just saying thank you.
Okay, welcome.
No.
Okay.